Okay, so today's talk is by Kevin Aguyar Brix, and his title you see there is Normal Coactions Extend to the C-star envelope. Please, Kevin, go ahead.
Thank you. Yeah, so first of all, thanks to Gisela and Cortinas for inviting me here. I'm very happy to speak in this seminar. And as you said, I'll talk about normal coactions. This will be normal coactions on operator algebras and how they extend to their C-star envelope. So I'll try to make sense of all that. And this is joint work with Chris Bruce and Adam Dor-On. So Chris and I are both based in Glasgow, as you some affiliation here is Glasgow, and Adam is at Haifa University, and he was visiting us earlier this year, and then we started this collaboration. So this is the work that I'll discuss here. And I was the overview. I was planning on dividing this into roughly two parts, and maybe spend half the time on each. So maybe short of half an hour on each part. And they're sort of separate, but then you'll see that they connect in the end. And some of these things are perhaps a bit technical, but I've really tried to make an effort to not dive into technical details and try to keep the main ideas clear. And so please ask if you have any questions. And I don't see any pictures of you, so please just interrupt or if there's anything. So the first part will be on operator algebras more or less in general, and I want to talk about symmetries. And when I say symmetries, you should think of actions, or in this case, coactions on operator algebras. And I'll talk about this result, which is contained in the title. And then for the second part, I want to move into a particular class coming from category theory. And we'll get to that point. So they will seem sort of separate, but then hopefully they'll tie up in the end. So beginning with symmetries on operator algebras, I want to start off with just giving the main theorem, which is already, you've seen it in the title already. So I'm considering an operator algebra, and our main theorem in this work with Chris and Adam is that if you have a normal coaction on this, then this extends to its C-star envelope. And I'm not expecting you to understand this statement as it is. I'll spend the whole time making sense of what all these things mean. But I just wanted to flash it here, and then you'll see when I show it again. Hopefully, it makes more sense. So a short motivation for what we're doing is this is a non-commutative geometry seminar, and this topic that I'll talk about is a non-commutative version of something commutative. So this is the basic example in function theory where you take the disk algebra. So here you want to think of functions on the open disk that are holomorphic, but they extend continuously to the closure. This disk algebra is a commutative Banach algebra, and there's a whole theory, function theory, about how you compute certain boundaries of such algebras. And a boundary should be understood in the sense of it's a subset of the character space of the algebra on which the functions attain their maximum value. So in this concrete example, we have these functions that are really supported on the open disk, but they extend continuously to the closed disk. And by the maximum modulus principle, such functions attain their maximum on the circle. And here you really want to think of the circle as the boundary of the closed disk. And so it is a boundary in this formal sense, and it's actually also the smallest such boundary. So this is what's called the Shilov boundary in this theory. And Arvidsson, dating back to work in the late 60s, and I think all through his career, was very energetically pioneering and popularizing this notion of a Shilov boundary, but also a non-commutative analog of this. And this is what we call the C-star envelope. So if I look at the same kind of example now, but in the dual picture, then I first start with the unilateral shift on Hilbert space, L2 of n. And we know that the C-star algebra you get here is the tuplets algebra. But in fact, so that's a C-star algebra. But if I'm interested in an operator algebra, so I'll say more about this, but an operator algebra is not necessarily self-adjoint. So I'm just interested in what happens if I generate an algebra, not a C-star algebra, but a closed algebra of this same information. I actually get, in this case, something that's isomorphic to the disk algebra. And then the analog of asking for this largest, the smallest boundary is asking for a quotient, the largest quotient I can find that contains an isomorphic copy of this algebra. So in this case, I take my tuplets algebra and I mod out by the compacts.
Sorry, may I interrupt you? What's the I?
Yeah.
What's the I?
Sorry, the identity.
So it's generated by the identity and S.
Yes.
S star.
No, not S star.
Okay.
Only
and
S.
then you complete it.
Yes, exactly. Exactly.
Okay.
So it's very important.
Like
That's exactly an important point.
Yeah.
That I don't take the adjoints because I'm in the operator algebra setting. I don't expect to have adjoints. So I'll be careful to distinguish between those two settings. And the point is just if you have this operator algebraic perspective, you can look at the disk algebra, and then the quotient of the tuplets algebra gives you, as we know, the functions on the circle. And this is in complete analogy with the circle being the Shilov boundary when you look at it from the function theoretic point of view. So in this case, we call this the C-star envelope. It is a C-star algebra, which is in some sense the smallest one containing the original data. So the important observation is that this quotient map actually takes the disk algebra to an isomorphic copy of it inside of the quotient.
So, sorry, algebraically, isn't this like the inclusion of the polynomials in one variable into the Dor-On polynomials?
Yes, that sounds right. Yes, yes. So this is just, I'm just rephrasing exactly the same thing in these two. This is the same example, just seen from two different pictures. And it's just to say that there is a whole industry of what is the Shilov boundary or what is the C-star envelope of an operator algebra. So I'll try to start from the basics now. And this is what I'll talk about. This in this case, we recover this this known thing in the commutative setting. But you can look at all kinds of operator algebras and then try to study what are their C-star envelopes. And there's Arvidsson conjectured there's many open problems related to, if you understand the C-star envelope, you can use that to actually study the operator algebra. There's dilation theoretic consequences and important conjectures that I can't spend too much time on now, unfortunately, but my emphasis in this talk will be the question of identifying the C-star envelope. So given a concrete operator algebra, how do you identify the C-star envelope? In this case, you just get the circle. So I think I've maybe already said it, but in operator algebra now, it's not assumed to be self-adjoint. So it's just an algebra. And I want to think of it as concretely represented on Hilbert space. And then Arvidsson's idea is that you can actually use C-star algebras to study the non-self-adjoint operator algebras. And the first step is to make sense of what a C-star cover is. So, I mean, whenever you have A on a Hilbert space, you can take a C-star cover of it. So this is a C-star algebra, an honest C-star algebra that contains an isomorphic copy of A. So it should come equipped with completely isometric homomorphism. So there's an isomorphic copy of A sitting inside of C, and then we call C a C-star cover. And then what I've already mentioned is a C-star envelope. You really want to think of this as the smallest C-star cover of an operator algebra. So formally, the way we have to make sense of this is to say that I have my operator algebra, and the envelope denoted like this should be a C-star cover. So there is a completely isometric homomorphism sending in A into this. But whenever I have another C-star cover, there should be a unique surjective star homomorphism from C into the envelope. And this is what we refer to as a co-universal property. So in C-star theory, a universal property for some generators and relations, say, would say that if you see these generators and relations in some other C-star algebra in the wild, then you know you have a homomorphism going out of the universal object into this other thing. But a co-universal property is one that attracts a homomorphism. So that if I have a different C-star cover, I know that there is a homomorphism going into my envelope. So this is how we make sense of the C-star envelope being the smallest C-star cover. And just like for universal properties, this actually tells you that the C-star envelope is unique up to star isomorphism. So we'll just refer to it as the C-star envelope.
Oh, sorry, it's
So
somehow like the property that the multiplier algebra has, that it goes the other way too.
well, in what sense? The multiplier algebra has
So if you embed A into an algebra as an ideal, then this algebra
yeah.
maps to the operator algebra, to the multiplier algebra in that sense.
I'm not sure I understand.
I mean,
What role does?
no. I mean, the arrow points in the same direction, right? So if you embed,
Okay.
so it's an
Okay.
arrow.
Yeah.
I mean, it's not like justifying that it's not the first time one has seen
No,
that
certainly.
property, because, for example, the multiplier algebra has the diagram that you draw is
Yeah.
similar.
Right. And any injective object would have this property. If you want to generalize this, but I mean, co-universal properties are all over. This is exactly as you say, an instance of this. This is not the only place. Definitely. Okay, so if I'm trying to push this idea of trying to compute the envelope, so I want to flesh out how you would do that. And in practice, you'll take 3 steps. So you start by having a candidate for what the C-star envelope should be. You'll show that it's a C-star cover as step 2. So this just means that it contains a copy of A. And because of the co-universal property, if C is a C-star cover, then you get this map automatically. And step 3 is then to check that this is actually injective, because then you'd have an isomorphism and then you're done. You have found it. So this will be the guiding thread throughout the talk, these 3 steps. Now you'll see them again. So let me just spend very briefly say that there's been a lot of work going into doing this. So Arvidsson started this whole thing, and there's many players on the field that have contributed. And this is by far not a complete list, but I just wanted to mention a few. So, for example, if you have a C-star correspondence, then you get a canonical tensor algebra, which is the algebra that's generated. So from the C-star correspondence, you get a Fock module, and you generate a tensor algebra from the creation operators. And the question is then, what is the C-star envelope of this tensor algebra? And some work started with Muley and Solel and some others, and Katsoulis Cripps then finally showed us that it is actually the Kunz-Pimsner algebra of the that is the C-star envelope. So it is somehow what you would expect. And this was then finally showed by Katsoulis and Cripps. And you'll notice this is just after Katsura's 2004 paper, where he makes C-star correspondence much more flexible. Of course, it originates with Pimsner, but Katsura makes it much more flexible. And then if you want to go into more general cases, then C-star correspondences generalize into product systems. And then C-star correspondences, you can think of that as indexed over n. And a product system is then indexed over a more general monoid that's embedded in some group. And just like you can in this case of C-star correspondences, you can generate what they call a tensor algebra. So this is, again, an operator algebra, not necessarily self-adjoint. And then there's been a lot of work with increasing generality on understanding what the C-star envelope of the tensor algebra is. And the increasing level of generality comes from, at least one aspect comes from which group the monoid embeds into. So in this 2020 paper from Dor-On and Katsoulis, they assumed that you were embedding into an abelian lattice ordered group. In this Kakariadis, Katsoulis, Lee, Laka, there's a more different class of group embeddable monoids. And then Camila Senem sort of resolved the whole question for all group embeddable monoids in her recent work, identifying what the C-star envelope is of the tensor algebra of a product system. And I really don't want to go into what a product system is. It's a high dimensional or a generalization of a correspondence. That's what I'll say, but you can make sense of a canonical tensor algebra inside of that. But one thing I want to emphasize is that there is a work of Dor-On, Kakariadis, Katsoulis, Lee, and Laka, and they say the turning point in our investigation is the realization that a product system over a semigroup P in a group G, if you do this, then the tensor algebra comes equipped with a natural normal coaction of G. So this goes back to the initial things I said, this kind of symmetry. There's always a coaction in the background, and in this case, it comes from the group that P embeds into. So I don't want to go into the details, all I want to say is that in all these very general cases, there's always a normal coaction lurking in the background. And this is said explicitly in their work here. And actually, they're also able to say that this problem of identifying the C-star envelope in all of these cases can somehow be distilled into the question of when a coaction on this operator algebra, which they observe always exists, when does this extend to the C-star envelope? Somehow they're able to condense this question into this, computing the envelope into this question. And this is what we make a contribution to answering this question. So obviously there's much more to be said about this, but in the interest of time, I can't do fully justice to this. But okay, so hopefully I've motivated the fact that for this very large class of systems, there is always coaction in the background, and there's an important question that concerns whether this coaction extends. And this is in order to compute this, to find a description of this envelope. So let's actually dive into it. So what is a coaction? If you are content with abelian groups, then coaction, you can equally describe it as an action of its dual group. But the point is to go beyond abelian groups. So we have to somehow, we can't avoid it. And so you dualize the whole notion of an action, and in this case, a coaction on an operator algebra A is a homomorphism, a completely contractive homomorphism into this tensor product of the full group C-star algebra. And it should satisfy this property that if you take the spectral subspaces, so they look like this. Here, the UG is the unitary associated with the group element G. Then the spectral subspace is exactly the elements where the homomorphism behaves like this. And if you sum up all those spectral subspaces, this should be dense in the original operator algebra.
Sorry, some question.
Yeah.
I'm quite ignorant about general operator algebras. So is the tensor product a tensor product that is defined in the category of operator algebras?
It's all spatial. It's all spatial.
Okay.
I mean, there is an abstract notion of operator algebra, but to be safe, I'm always assuming it's represented on Hilbert space.
So you tensor, it's represented, you tensor it, you represent it in a tensor product in space and take the closure. Is that what you mean by space?
I guess, yeah. Yeah.
Okay.
So it's all concrete. That's my point.
And
it's
you don't, sorry, you do not need to put the multiplier algebra somewhere, because it usually appears when one defines coactions of sister algebras.
No, I don't. Maybe what you're thinking of is there's a lot of literature on locally compact groups and coactions in that setting. And that's where the multiplier appears. But we only work in the discrete case, so things simplify. But that's definitely true. There's a very nice memoirs paper that talks a lot about coactions and C-star algebras that they need multiplier algebras all over. So in our case, this is a general coaction, and we actually want to, if you might have noticed, this normal appears. And I mean, normal is of course a bad word because it doesn't say anything. But the condition for a coaction to be normal is that this composition, so I take my original homomorphism and then I map it onto the reduced group C-star algebra instead. And this map should be completely isometric. That's the condition. And if you want, you should think of this as a reduced coaction instead. There's a subtle difference formally between the two, but we show that they're in principle the same thing. So if you want to think reduced instead of normal, please do that. And this is the setting I want to be in, normal coactions. And of course, if the group is amenable, then any coaction is normal because then you just have the identity here. So this is the setup. And then...
Can I have a question?
Yeah.
To this previous slide. So you don't assume that coaction is by definition, this map delta is injective.
I assume that it's completely...
So normal coaction would be completely isometric, I guess.
I think this is a typo. Sorry. Now I'm certainly not sure. I'm actually now I think I want this to be isometric, but now I'm doubting. Might be a typo.
But anyway, if it's completely isometric after projecting down to the reduced sister algebra, it cannot be 0 cent.
Yes. I think this is a typo.
And do you think that I mean, am I right in thinking that what you want is a reduced coaction that lifts, but you are interested in the reduced version?
You can think of it like that. I mean, I'm in essence, I'm only interested in the in this map, the delta lambda, really. Yeah. I'll try to be very brief with this next thing. So I want to get back to our theorem and then spend a few minutes on our proof. And our proof uses a Katayama duality for operator algebras. So maybe let me jump directly to what this statement is. If I have an action on a C-star algebra, then I can take the cross product and then there's an induced coaction on the group component of that cross product. So I can do the action and then the cross product by that coaction. And or if the group is abelian, then I get a cross product action and then an action by the dual group. And this doing two cross products is you actually obtain the original C-star algebra up to tensoring with the compacts, and this is Takai duality. If you flip the order, so you first take a cross product by a coaction, and then the induced action you get on the group component, you then take the cross product by that action. So first coaction and then action. Katayama was the first to show that in this case of C-star algebras, again, you get something isomorphic to the original C-star algebra up to tensoring with the compacts. And so what we needed for our proof, and I'll get to that in the next slide, is exactly this statement, but for operate algebras. So this thing is well known and studied for C-star algebras, but we needed it in the case of operator algebras. And I should say the proof is, if you understand the C-star proof, then you roughly understand the operator algebra proof. There's basically no surprises. There's only a few places where you need to be slightly careful. But it's very nice that you have this. So it sort of tells you that the operator algebra up to stabilizing with the compacts actually is a cross product. You can interpret it like this. And in order to in order to prove this, we have to make sense of what this coaction cross product is. This is not something we found in the literature before. And you can do that very concretely and spatially here. Let me skip the details now, but this is the concrete definition. So I just want to say that there is such a theorem, and the proof is roughly the same as in the case of C-star algebras. And then maybe this seems familiar because this is exactly the same theorem as I had in the beginning. So the question distilled in the case of product systems was whether a coaction extends to the envelope. And now we have a theorem that says whenever you have a normal coaction, then it does extend to the envelope. And it's nice to just have an answer that says yes to this question, but I actually think the proof is just as nice. And the proof is really contained in this diagram. So let me just spend 1 or 2 minutes trying to explain this diagram. You'll see in the bottom row, you have operator algebras, and the top row, you have C-star algebras. So if you start with your A and you assume you have a coaction on it, then you do the cross product, the coaction cross product, and then you do the cross product by the induced action. By this Katayama thing I just showed you on the previous slide, this is isomorphic to the original thing tensor the compacts. So this bottom row is just Katayama for operator algebras. And now I take the C-star envelope on both sides. So if the operator algebras are isomorphic, then their C-star envelopes are isomorphic. So I get an isomorphism up here. And now there's an observation by Katsoulis, a very nice theorem that tells you that when you do the cross product, this is an action cross product, reduced, then you can actually move the parentheses. So this isomorphism is Katsoulis' result that says that the envelope of the cross product is the C-star cross product. So we get these isomorphisms on the top row here. And now the observation is that here I have an action cross product. So then there is an induced coaction on the group component here. So this means this top right object admits a coaction that comes from this G component. And then I trace this back all the way back through these isomorphisms. And I also have a coaction coming from this group action cross product. Sorry, there's many things to keep straight in your head. And I trace this back to this component. So I've taken coactions on these rightmost components, and I've just traced them back all the way to the left here. So this means that these left-hand side objects now contain cross products. And if you follow the diagram around, you'll see that the map here is actually equivariant for this. And now you're almost done, because all you need to do is identify a copy of A inside of this. Remember, this delta lambda is assumed isometric, completely isometric. So A sits as a corner inside of this, and the envelope of A sits as a corner inside of this. So all you need to check is that these corners are invariant, and that this map then induces a map on the corners that is still equivariant. And so you just need to carefully check that, and then you're done. So it turns out you cannot use, well, we couldn't use Katayama duality for C-star algebras. We had to use it for operator algebras, and then induce an isomorphism at the level of C-star algebras, use Katsuli's result, and then trace everything back to our original operator algebra and the envelope. So we do this carefully in our paper, but the whole proof is really contained in this diagram, which I think is really nice.
I just one remark. It's key that in the Katayama result that you mentioned before,
Mhm.
the isomorphism happens in the category of G gray with aspect, because you use this, right? I mean, you use that. I mean, in the double cross product, you have a G action. You have a G gradient that is the coaction.
Yes, yes, yes.
Yeah.
You trace this back.
Yeah.
Yes, and the Katayama is very explicit, which is one of the nice things. So you can write down explicitly what the action, the coaction is here. It's, I mean, some complicated expression, but you could write it down explicitly. Yes. Okay, so this marks the end of the first part where I wanted to talk about general symmetries on operator algebras. How do you compute the envelope? And one final remark is to say that our theorem here really comes in step 3, when you want to show that something is injective. And this is because it's in general very difficult to check that a particular star isomorphism is injective. But when you have a normal coaction, you have a fixed point algebra, and you have a faithful conditional expectation onto that. So this gives you a new tool. If you can check that this map is injective on the fixed point algebra, you're done. So you need to have a candidate that also has a coaction, and then you can use the fixed point algebra of that. So that tells you this. So are there any more questions related to this before I move on to the second part? Okay. So this is, okay, I'll move on. The second part is now left-cancellative small categories. And I think I've prepared more than I have time for. Should I go until 55, or what do you prefer?
Well, I mean, yeah, just go on and we'll see. I mean,
Okay.
55 is fine, of course. If he has to go
Yeah.
to 11, it's fine too.
I'll see if I can. I mean, there's a lot that I'd like to say, but I'll have to restrain myself. So I think the first point I want to make is I wanted to give some examples to make this more digestible, because categories can be very abstract, and in general they are. But the way I want to think of them is really as monoids with multiple objects. So in particular, a monoid itself is a category with just a single object, just like a group is a groupoid with a single object. So the point is that I don't want to think of categories in general category language. I want to think of them as algebraic objects. And another example comes from directed graphs, where if I take the finite paths, then this actually forms a category. The range and source maps of the graph are the range and source maps of the category. And usually graphs are studied more concretely, but in fact, if you already go to the case of higher rank graphs, then they're defined to be categories. And they're defined to be categories with an extra property, namely that they admit a degree functor. And if you haven't seen this, you should just think of a degree functor as something that tells you what the length of a path is. But now, because it's higher rank, the length will be some vector in n to the k. And then it satisfies some unique factorization rule. That's not important. Oh, sorry. That's not important for now. my main point is just that you'll see these categories many places, and these are just very basic examples. There are many others, but one important one is the monoid, and the other important one comes from graphs. So I want to think of them as these algebraic objects, and just like for monoids or for groups, I have a left regular representation. But and this left regular representation is really just multiplying on the left. So if I take my element C and I look at L2 of C, then what it does to a basis element EX is just multiply on the left.
So L2 is L2 of the objects, right?
No, of the whole category.
Okay. So you
Yes.
take everything. Okay, yeah.
Yes. So think of this as a monoid, for example. Then, but then the important point is that the left regular representation, this thing, well, the formula makes sense, but it only extends to a bounded operator if I have cancellation property. So this is why I need this left-cancellative. And this really just means that if I have an equality like this, I can cancel on the left. And this is just a technical condition I need for this particular representation to make sense, to actually extend to bounded operators. So once I've done that, it's complete analogous to the case of monoids or the case of groups. Then the left reduced C-star algebra is this concrete C-star algebra on this Hilbert space generated by all these images. And in fact, you can sit down and work out their partial isometries. So just like for groups or for monoids, it's a C-star algebra generated by partial isometries. This is also sometimes called the tuplet C-star algebra, but I've chosen this terminology. And very important for this talk now is that there is not just a C-star algebra, but there is a canonical operator algebra. This is exactly the same thing. I generate by exactly the same thing, these images, but now I just look at the algebra and close it off. So again, I don't have adjoints necessarily in here. So a category gives me C-star algebra and an operator algebra sitting inside it. And this is the one now I want to study. I want to know what the envelope of this thing is. And here I'm being a bit technical. So what I did was that I had one technical slide, and then I had the next slide saying exactly the same thing, but without the technicalities. So maybe let me just, maybe I should skip to that. So this is exactly the same thing, but without all the technical details. If you want, we can discuss this, of course. The main point I want to get across is that there is a completely natural procedure for taking such a category and building an inverse semigroup and building a space of characters on related to this inverse semigroup so that I get a canonical action of this semigroup on this space. So let me say that again. There's an inverse semigroup you can generate by the elements of the category, and the elements you can make sense of each element multiplication by an element as a partial bijection on C, just viewed as a set. And from this information, you can generate an inverse semigroup. So it's concretely generated. And then the domains of these partial bijections is a space, and I can look at a particular collection of characters on that space. And the important thing here is not exactly how all these things are defined. The important thing is they're defined completely naturally from the starting data of the category. So I have this canonical action, and this action is such that it actually determines an ital groupoid. So you should think of this as a cross product groupoid.
So sorry, if suppose you have a cancellative monoid, right?
Yes.
Is the inverse semigroup some sort of group completion of the monoid?
Is the inverse semigroup what, sorry?
The inverse is the inverse semigroup in that case, starting with that C. Is it what can you describe it? I mean, the inverse semigroup generated by the monoid? universals.
It is generated by the monoid in the sense that every element, so every monoid element, defines a partial bijection on the monoid itself.
Yeah, what I mean is I suppose you can imagine that you can formally add inverses in the inverse group sets.
Yes, yes,
I'm
exactly.
asking whether
Yeah. So
that
you
is
do
what you
formal
mean.
inverses. Yes, and then in principle, so in I haven't written this, but a generic element in IL is then a finite product of such things and their inverses.
Okay, so there is no or condition. I mean, you do
Well,
not.
if you have that, then things simplify. Certainly,
Okay.
in general, you get these finite. But yeah, if you impose conditions, then things simplify a lot, and it gets much nicer. Yes. Yes. So my main point here is that, in general, I'm personally very interested in dynamical systems, and I think it's fascinating that you start with something very abstract like a cancellative small category, and then you do some constructions and you generate an état groupoid, or equivalently, you generate this action of an inverse semigroup on a space. And more than this just being fascinating, it's actually extremely useful, because this C-star algebra I told you about before, this concrete C-star algebra, if under very mild conditions, so for example, when the groupoid is Hausdorff, this groupoid is actually a model for this C-star algebra. So there are a few different conditions, one of them being Hausdorff, and when they are satisfied, there is a canonical isomorphism that identifies these two. This goes back to work of Spielberg, and Schindler has done some work recently as well. So this goes into this general idea of having some concrete C-star algebra, and in order to study it, you want a combinatorial model. In this case, it's a groupoid model, or dynamical or combinatorial model. So now I told you that I was interested in this C-star algebra and also the algebra sitting inside of it, the operator algebra sitting inside of it. And one way to approach it is now using groupoids through this construction. And then, in complete analogy with the observation from these 5 authors that I mentioned earlier in the case of product systems, we show that this C-star algebra always carries a normal coaction. And this normal coaction actually descends to a coaction on the operator algebra sitting inside of it. So this means that, again, I have to say this is a bit surprising, but in this very general setting, you generate this abstract dynamical system, and the operator algebra always carries a coaction. So maybe coactions are a bit esoteric, but they definitely turn up all over. And the question is whether you have enough tools to actually study them, to extract information. But they are all over. And we use the groupoid to, or we use this whole construction to conclude that there is a coaction. And then the next step is, so you notice I've gone into the 3 steps now of identifying the C-star envelope, and the first step is finding a candidate. And this space omega, I told you it was a space of characters, and then you can now look at certain maximal characters, or the boundary characters is then the closure of the maximal ones, but there is a particular subspace, and you can look at the quotient groupoid, and the C-star algebra of that closure groupoid is what we call the boundary quotient C-star algebra. So I realize I'm not giving you all the information to actually understand what all that goes into this, but I want to say that the space omega is built from the category, and now the partial omega, the boundary, is again just a canonical construction. So this gives us now a groupoid model for what we call the boundary quotient C-star algebra. And here, there was a workshop in Copenhagen in the autumn of 2022 where Xin Li gave a lecture series. And at some point, he posed this question explicitly. Given this operator algebra from a left-cancellative small category that I mentioned earlier, what is the C-star envelope of this? Could it be the boundary quotient? So Xin already answered step one here. He found a candidate for us. So this is where we came in and thought maybe we can actually answer this question. We have a concrete model for what the boundary quotient is. We understand what the operator algebra is. Can we now use our general theory about these coactions to answer this question? And this is what I'll spend the last few minutes talking about. So you remember that there were 3 steps. Step 1 was to find a candidate. Step 2 is to show that this candidate is a C-star cover. And this is one of our theorems. And then I'll get to step 3 in a minute or 2. Good. So if we look at this omega, which is the unit space of the groupoid, I told you there's this boundary of it, the boundary characters. And this canonical map that takes a C-star algebra to the quotient, this is the boundary quotient C-star algebra. What we showed is that this canonical quotient map is actually completely isometric on the operator algebra. What does that mean? It means that the operator algebra sits inside of this C-star algebra, but it's actually carried completely isometrically into this quotient. So the quotient contains an isomorphic copy of the operator algebra. This in turn means exactly that this quotient is a C-star cover, because it's a C-star algebra that contains an isomorphic copy of the original thing we're interested in. And we were very happy with this proof. It's actually it's a really nice proof, I think. And we thought we could do it in the general setting of left-cancellative small categories. Then at the very end, we found an issue that we couldn't get out of without assuming cancellation. So when I say cancellative, I put a line under here. It means that it's both left and right cancellative. And this is, I mean, it's not a serious restriction, but it's an interesting question whether it's necessary. We don't know. At least our proof doesn't work the way we see it now without assuming both left and right cancellation. But the fact that this quotient map behaves nicely with respect to the operator algebra tells you that this thing is a cover. And now by the co-universal property, there's a canonical map that goes into the envelope. And now the question, of course, is, this is nice, but when is this map injective? When have we actually identified the envelope? This is the question. And I wanted to say that this took a lot of work to prove this theorem, and it goes, the main idea was inspired by this work of Dor-On and Katsoulis. I don't have time to talk about it now, but it took some work. Good. So we're in the situation now of having this general surjective star homomorphism. When is it injective? And there are some, this is the same question. There are some straightforward answers. For example, if the domain is simple, because this is a non-zero map. So if the domain is simple, this has to be an isomorphism. But also, if we try to take advantage of this being a groupoid C-star algebra, if the groupoid is effective, this has the consequence that the C-star algebra, any ideal in here will be detected by its diagonal subalgebra. So these are the functions on the boundary characters here. And a separate lemma we show is that this map is actually always injective on this diagonal subalgebra. So if the diagonal detects ideal in the big thing, then we can bootstrap injectivity from the diagonal up to the whole thing. So these two conditions are very general conditions, and they're very nice, of course, but the issue is it's in concrete examples, it's very difficult to verify when they're actually the case. But the third bullet is what I want to emphasize here, where we actually use the coactions. So if I mentioned this before, that because everything involved here carries a coaction, then there is a fixed point algebra, and it's enough, by general theory, it's enough to check injectivity on the fixed point algebra. And one corollary of this is that if lambda is a finitely aligned higher rank graph, then this map is injective. And this is simply because we can, this is simply because we can identify the fixed point algebra. And we can, once we've identified it, we can infer that it has to be injected. And another instance is then maybe our second main result, is that we have an affirmative answer. This thing is actually an isomorphism when we assume that our original category embeds in a groupoid. And this may sound like a weird or strange condition, but if you think of monoids, this is really very natural. A monoid, in the case of all these product systems that I mentioned in the first part, all the product system construction only makes sense when P is embedded in, the monoid is embedded in a group. So this is the natural analog. If you look at a category, when is it embeddable into a groupoid? And it turns out that if this is the case, then all our conditions are satisfied automatically, and we can understand the fixed point algebra of this coaction, and it turns out to be the diagonal. And we know that the diagonal, the map is already injective on the diagonal, so this thing is an isomorphism. And I should say that in the case of a monoid that is in group embeddable, our proof actually gives a very simple and conceptually nice proof of this fact. This was already in Camilla Senem's work, but our proof is very different and much shorter, I'd say. It doesn't use product systems. Good. This is what I already said. This is because we can identify the coaction fixed point algebra. That's the reason why we can conclude this. Good. So I'm done now, and let me just summarize that the main point of the first part was that our main theorem tells us that if you have a coaction on an operator algebra, it always extends to the envelope. We know that there are coactions on product systems, but I also told you that if you have this very general setting of a left-cancellative small category, then you have a coaction, and the boundary quotient is a C-star cover. And then finally, if the category embeds in a groupoid, then we can identify the envelope with the boundary quotient. And then there are still some interesting perspectives. For example, is this always the case? I mean, we have conditions in order before we can conclude that the boundary quotient is the envelope. Is this the case more generally? We don't know. We can only show this lifting result, extension result for normal coactions. But what happens if you have a coaction that's not normal, for example? This will have consequences for dilation theory. So there's many different perspectives you can take from this. But let me stop here, and then I'm happy to take any further questions.
Okay, thank you very much, Kevin. Are there any questions from the audience?
Do you have anything to say for when the group is a topological group?
No. Short answer is no. Our categories are always discrete. So do you mean when, let's see, do you mean when the monoid is embedded in a topological group?
Yeah, for instance, yeah.
Okay. No, I can only say I don't know, but that's definitely one of the perspectives I could have put here. What happens in the topological setting? Yes. Thanks.
Okay.
So,
Hi,
Daniel.
hi, Kevin. Thanks for the talk. I was sort of curious along the same lines as the previous question, but I guess more related to extending the coaction. You work particularly with discrete groups there. Are there any results along the line for locally compact groups, maybe locally compact abelian, I don't know, similar analogous results, you know?
Right. So in the abelian case, you can get by with just studying, as I understand it, you can get by with just studying actions, because then you have a dual group and
Right. That's your coaction.
yes, so you don't need to go into coaction business. So, but yeah, again, I think I have to say I can't say anymore, but it's definitely an obvious question. What happens when I have? Yeah, no, I think I can't say anything else other than that. It's an interesting question. What
Thank you.
happens?
Any more questions?
Yeah, I wanted to ask about this assumption that your groupoid is Hausdorff. How strong is this
Yeah.
assumption? And why it is so important, maybe?
Good. It's definitely important for our proof. And why? That's because maybe I can go back to this. So we're interested in this concrete algebra, but the way we approach it is using the groupoid. And one thing we need is that this thing is an isomorphism, and this is not known to be the case always. One condition for when it's known is when the groupoid is Hausdorff. But this is, again, a very interesting question. What happens when you're not Hausdorff? For example, the class of self-similar actions. In the case of self-similar actions, you can expect it to be Hausdorff. What happens there? We need it here to identify these two, but we need it in a few steps in the proofs as well. So for now, we can't get rid of it.
Thank you.
Further questions? If not, I have one. If
Okay.
when so you take this, say your category is a mode, and then well, you make a semi-group, an inverse semi-group out of it. Yeah, so this omega, well, so I don't know if it was the omega, but then you take the action of the inverse semigroup on the character space of its idempotence, right?
Yes, a subset, but yes.
Well, yeah, so that will be the boundary. So, but what you get is this, by any chance, what Excel calls the tight, the universal.
Yes, good. Thank you. I forgot to say that. Yes, the omega, no, sorry, the partial omega, the quotient is the tight groupoid of that groupoid. Sorry, the tight. Yes.
So is that
So it just.
general fact?
Sorry.
Is that the general fact? I mean, with a C you associated some inverse semi-group that you called something like IL of C or something?
Yes, exactly.
It's always true that it's the tight sisterage of this thing, of this inverse semi-group.
I think for this groupoid, it's always the case. I think in Xin Li's paper, I think he says that explicitly, that it is, you can identify it with this. So this whole machinery of Excel and Excel Pardo, you can definitely use that to understand this. And we do that in our proofs. It's I just forgot to say it. So thanks.
Excellent. I mean, okay. So I know that this monograph by Excel, and then
Yes.
I have the Excel Pardo papers, but I don't know. I mean,
yeah, I mean, somehow what Shin does is, I think that the Excel Pardo deals with the very general case of inverse semigroup actions. and they give conditions for when the groupoid is one thing or the other, when it's Hausdorff, when it's
Yeah.
and Shin specializes to some of the example classes that he's interested in. But still, these characterizations can be very complicated.
Okay.
So
So I'll stop the recording now.